Hey guys, welcome back to lecture series on linear differential equation with a constant coefficient, which is from EM3. So already in my previous lecture I explained to you all Cauchy's homogeneous linear differential equation complete method with some of the example. So in our today's lecture we are going to learn new topic, which is a Legendre's linear equation. Okay, Legendre's linear differential equation, which is a extended form of a Cauchy homogeneous linear differential equation. Okay, now see that I written here that a Cauchy homogeneous linear differential equation a naught x raised to n d raised to n y by dx raised to n plus a1 x raised to n minus 1 d raised to n minus 1 by dx raised to n minus 1 up to so on a and y, okay, which is equal to phi of x. This one is our Cauchy homogeneous linear differential equation. In my last lecture I explained to you all how can we solve this example. Okay, how can we solve the solution for this Cauchy homogeneous linear differential equation. So in my today's video I'm going to explain to you all a Legendre equation. Okay, so Legendre equation, it is actually extended form of a Cauchy homogeneous linear differential equation. Okay, the extended form of this Cauchy homogeneous linear differential equation. What means by extended form? What happen if that x get replaced by some another values? Means instead of a x, if you get some another like a x plus by plus c z plus d or any another equation. Okay, yes, so instead of x I'm going to replace here some another values. Okay, so if I replace x as x plus b, consider I am going to replace x as ax plus b. Okay, replace x as a x plus b. I'm going to replace x over here as a x plus b. So everywhere, wherever you get the x. Okay, so replace x as a x plus b. Then let's see what we get here. A naught, okay, a naught ax plus b, okay, a naught ax plus b raised to n, okay, power n keep as it is, raised to n d raised to n y by dx raised to n plus a1 x raised to x plus b raised to n minus 1 d raised to n minus 1 y by dx raised to n minus 1. Okay, this one is the substitution of x only as a x plus b. Okay, plus a n minus 1 x as a x plus b, so ax plus b dy by dx plus a n y, which is equal to phi of x as a x plus b. Okay, we're replacing x as a x plus b over here. Okay, so this one is the complete replaced term here. Okay, now see that when I replace x as a x plus b, then we get some special type of the linear differential equation, and we call this as a Legendre. Okay, we call this as a Legendre's linear, okay, differential equation. We call this one as a Legendre's linear differential equation. Okay, yes. So as you can observe, a naught, a1, an minus 1, an, all are the constant. Okay, a naught to an, all are the constant. So whenever we have x plus b raised to n everywhere present in our Legendre's differential equation, we have to go for some substitution, as we have done it here in our Cauchy homogeneous linear differential equation. When we have x here, we replace x as a e to the power z. Okay, what we replace here, x as a e to the power z. So similarly I'm going to replace that ax plus b. Okay, put ax plus b as a e to the power z. Okay, in our previous part, Cauchy homogeneous linear differential equation, we replace x as a e to the power z, but instead of x we have here ax plus b. So we are going to replace x plus b as a e to the power z here. Okay, so find out the value for z, apply log to the both side. So log of x plus b, okay, log of x plus b, log of e to the power z, so it remain only z. Okay, log and e it will cancel, then it remain only z here. Okay, log of x plus b which is equal to z. Okay, so this one is the value for z. So what we need more? The value for dz by dx. Okay, you can go for finding the dz by dx using this one also. Okay, so what is the dz by dx? Dz by dx need to differentiate this term. Okay, log of x having differentiation 1 upon x. Okay, 1 upon x means 1 upon x plus b. Okay, and after that this one is a function. Okay, so apply the Cauchy theorem, okay, for finding their differentiation. Okay, now what we do? Differentiate that x plus b later on. X plus b differentiation, it remain only a here. Okay, so a upon ax plus b, which is a dz by dx over here. Okay, this many value I found it here. Okay, yes. So let's go for finding the substitution values here. Okay, so what we need to substitute that nth power, n minus 1th power, and up to the first power. Okay, so what we have to replace, we'll figure it out here. Okay, yes, I hope you all have understood up to this step. Yes, now I'm going to expand dy by dx. Okay, here we have dependent variable is y and independent variable it is x. Okay, so I'm going to expand with respect to z differentiation. Okay, that means I'm going to differentiate y with respect to z, dy by dz, into again that z with respect to x, dz by dx. Okay, this one is chain rule for differentiation. Okay, so dy by dx, which is equal to dy by dz into dz by dx here. Okay, yes, this value I got it here. So the next step, what we write, dy by dz, replace dy by dz here. So we want dy by dz or dz by dx, as we don't have dy by dz but we have dz by dx. Okay, replace dz by dx instead of it here. So dy by dx can be written as dz by dx. What is the value? A upon ax plus b. Okay, a upon ax plus b, and dy by dz. Okay, so what we have here, a upon x plus b, which is equal to into dy by dz. Okay, so we are going to find out the value. Take ax plus b to the other side. Okay, so we write ax plus b into dy by dx, which is equal to a into dy by dz. Okay, what I have done, I taken that denominator to the numerator over here, keeping a as its own place. Okay, yes. So what is the value for dy by dz? Also remember that d by dz we always substitute d by dz as a capital D. Okay, yes, d by dz as a capital D. So I'm going to write ax plus b into dy by dx as a into dy. Okay, that means d by dz I substitute the value as a capital D here. Okay, a constant as it is, y out here. Okay, so ax plus b dy by dx, which is equal to a into capital D y here. Okay, yes, so this one is the value. Whenever we have x plus b dy by dx, then you have to replace a into capital dy. Okay, that means see that x into dy by dx. Okay, x into dy by dx. Instead of that, we have here now x plus b into dy by dx. In such a case, you have to replace the value a into capital T y over here. Okay, yes. Similarly, go for the double differentiation. When we have double differentiation like a d square y by dx square. Okay, whenever we have double differentiation, we write d square y by dx square. Take 1 by d by dx outside. Okay, and dy by dx inside here. Okay, so that means I taken one derivative out here and remaining kept inside here. Okay, yes. So put the dy by dx here. What is the value for dy by dx? You can see that dy by dx here, dy by dx is equal to a into dx plus b upon dy by dz. Okay, yes, put this value here. Then we get the d by dx of under bracket dy by dx. What is the value for dy by dx? A upon ax plus b. A upon ax plus b. A upon ax plus b dy by dz. Dy by dz. Okay, yes, which is the value for dy by dx over here. Okay, yes, what we do here now, we are going to differentiate these two terms. Okay, now see that this one look like one function, it is another function, so between them we have multiplication. So what we do, we take differentiation with respect to x by applying by part rule for differentiation. Okay, so we are going to apply by part rule for differentiation, and what it say that keep first term as it is. Okay, first term as it is means a upon x plus b as it is. Okay, a upon x plus b as it is. Differentiation of a second term. Okay, that means differentiation of a dy by dz with respect to x. Okay, d by dx of a dy by dz. Okay, so what I have done, I kept first term as it is, differentiation of a second term, plus second term dy by dz as it is. Okay, second term dy by dz as it is, differentiation of a first term a upon ax plus b. So how can we define a upon ax plus b, differentiation of a upon ax plus b? As we know that d by dx of 1 upon x, what is the d by dx of 1 upon x? Which is a minus 1 upon x square. Okay, so consider this term as a x. Okay, 1 upon x, differentiation of 1 upon x is a minus 1 upon x square. That means x plus b bracket square. Okay, after that differentiation of x plus b later on, then we get the a here. Okay, and previous a, that means it goes to the a square. Okay, that means you need to know how to find out the differentiation a upon ax plus b. It is way easier. Okay, so what we do, we keep a as it is first. 1 upon x has differentiation minus 1 upon x square. Okay, that means x plus b square, and later on differentiation x plus b, which is a only. Okay, a into a minus a square. Okay, this one is the term. So in our next step, what we do, we take a similar term out from here. So here we are going to write this step, d by dx as a dy by dz. See here carefully, keep that a upon x plus b as it is. Okay, d by dx of a dy by dz. So we take differentiation with respect to d by dz. Okay, d by dz. Okay, so we take differentiation of a d by dz and dy by dx. Okay, so after that we are going to differentiate this one. Okay, so dy by dz. Okay, dy by dz, and then dz differentiate with respect to x. So dz by dx. Okay, so I just differentiate dy by dz with respect to d by dx here. Okay, so you can replace, otherwise you can replace the values also. Okay, plus next step we get here dy by dz. Okay, as it is, minus a square upon x plus b bracket square. Okay, now see that this step I kept as it is here. Okay, now we are going for further calculation. Yes, now see that dy by dz into dz by dx. Okay, dy by dz into dz by dx, which multiplied by x upon a upon ax plus b. Okay, so we write a d square y by dz square. Okay, take that dz into dz, that means make that it is double differentiation a upon ax plus b. Okay, so d square y by dz square. Okay, d square y by dz square it is coming here. Okay, so a upon x plus b as it is, d by dz. Okay, so d by dz into dy by dz, that means d square y by dz square and dz by dx. So we are going to replace the value for dz by dx. Okay, so what is the value for dz by dx? Now see that here, which is dz by dx is a upon ax plus b. Okay, so replace that one here, a upon ax plus b. Okay, a upon ax plus b. Now see that I replace that dz by dx over here. Okay, plus dy by dz. Okay, dy by dz into minus a square upon ax plus b bracket square. Okay, this one. Now see that a upon x plus b, a upon x plus b, that means we get it here a square upon x plus b bracket square. Again that one term it is here, take both similar term outside here, then we write outside a square upon ax plus b bracket square. Okay, a square upon ax plus b bracket square. Between these two terms I taken these two out here. Okay, that means this one into this, that it goes to the square. Remaining term here d square y by dz square minus as it is dy by dz. Okay, this one is the next step we got it here. Okay, yes, now what do we do, this one is the actual value for d square y by dx square. Okay, when I solve d square y by dx square, I got this one. Okay, so what do, we take this step to the other side. Okay, so x plus b bracket square. Okay, which is a x plus b bracket square into d square y by dx square, which is equal to a square into this entire step. Okay, yes, so we are going to do some of the adjustment here. Yes. So what I'm going to do here, see very carefully, ax plus b bracket square, okay, ax plus b bracket square. So d square y by dx square, okay, d square y by dx square can be written as a square, keep as it is, okay, under bracket. Now see that what I'm going to do, d square y by dz square, that means d square minus dy by dz minus d, okay, d square minus d, and out of bracket y here, okay. That means I am going to write this one as a square into d minus 1 into d into y, okay. Now see that whenever we have x plus b, okay, the term which present here in our equation, x plus b bracket square d square y by dx square, which is equal to, then we have to replace with the value a square into d minus 1 y, okay. So what happened when we have cubic part? So in the condition of a cubic, like when we have third differentiation with the ax plus b bracket cube d cube y by dx cube, okay, in this form, if we have, okay, if you have the value in the form of x plus b cube plus d cube y by dx cube, okay, these are the terms from Legendre's differential equation, okay. So we are trying to replace this term with some another form of a d, okay. Yes, so ax plus b cube d cube y by dx cube, we can write it as the a cube, similarly generalization by second power, okay. So d into d minus 1, okay, into d minus 2 into y, okay, d into d minus 1 into d minus 2 into y, okay, this one and so on, okay. You can replace similar like this, okay, later on also. So these are the values that we have to replace whenever we have x plus b instead of x, okay. Whenever we have x plus b present in our given example, then replace these values, okay, just in order to convert our given Legendre differential equation into the auxiliary equation, then proceed with the complementary function, and then at the end particular integral, okay. This one is the entire process for finding the solution using Legendre differential equation, okay. You can see it here for your reference, okay. So this one is the entire process. So I hope you all have understood my today's entire lecture. It is completely based on the Cauchy homogeneous linear differential equation, which is the extended form of a Legendre's differential equation, okay. This one is the extended form Legendre's differential equation. So we learn in our today's lecture how to solve Legendre's differential equation by using substitution of ax plus b, okay. So in our next lecture we are going to continue some of the example based on the Legendre's differential equation. So till that we come again with the some of the similar lecture here in our channel, okay. So if you have any doubt, difficulty, let me know in my comment section, guys. I will come up with the similar video. So thank you everyone, thank you for my today's lecture.